Today's lesson we're going to talk about a concept called bond polarity. Now, in order to address bond polarity, we have to think about the fact that, remember, we're talking about covalent bonds. So we're talking about sharing a pair of electrons between two atoms. And if we're talking about an ionic bond, we're talking about electrons transferred from a metal to a nonmetal. Now, we're going to focus on this term right here, sharing. And when we talk about bond polarity, we're talking about the idea that there is kind of degrees, if you will, of sharing. In other words, sharing can be equal or unequal. Okay, so I use the analogy, okay, if you ever, when you were a little kid and you got some piece of candy or something from somewhere, like a candy bar, and then you brought it home, like maybe a prize from school or something, and your parents said, well, you should share that with your brother or sister. And chances are that, you were probably a pretty good kid and you did what mom and dad asked. However, you might have just broken off a little corner and given it to your brother or sister. And of course they would complain, but you say, but I shared. You didn't say it had to be equal. I didn't have to give them exactly half of the candy bar. Well, atoms can kind of be like that too. Even though they're sharing a pair of electrons in order to reach a lower energy state, not all sharing between two atoms is going to be equal. Now, how do we know which atoms, how do they share? How do they determine if the sharing is equal or not? Well, that relies on something called electronegativity. Electronegativity is a measurement of the ability of a particular element to attract electrons of another atom. Not its own electrons, but somebody else's electrons in it. And so if you're attracting it, you're pulling it towards yourself. Now, the measurement is actually on what you have your electronegativity table. Now, I have one to show you here. It may not be exactly identical to the one that I gave you to use as a handout, but it works. Okay, so if you look here, okay, looks like the periodic table, but the values that appear inside the box, those values are the electronegativity values. Now, you'll notice that there's kind of a trend or a pattern. This periodic table is full of trends or patterns. Remember, these are the metals to the left. Okay? Up here is a little kind of a drawing showing, if you look by color coding. So elements that have high electronegativity values, ones that are very strong attractors, are kind of coded in the orange, pink, and red. Ones that are poor attractors are coded in the kind of the purpley blue areas, and ones that are kind of in betweenish are kind of green and yellow. Now you'll notice that most of the blue to purple elements are metallic. Okay. Now there's no information here for these. That's because these are noble gases. Now remember, krypton and xenon do actually form compounds. Okay? They don't form very many compounds, but they form a few. And you'll notice that they actually have relatively strong electronegativity values if they actually manage to form a compound. Okay, so these are our poor attractors. And you notice that the red is, okay, most of the bright color here is kind of this roughly in an L shape here, the non-metals. Okay, so, and the noble gases, most of them have no values at all. So what we're going to be looking at is we're going to use the electronegativity table to look at the possible bond between two different elements on the table, and we're going to classify it in one of three ways. The first way that we're going to classify it is ionic. Now, you remember the ionic bond. Okay, this is no sharing. No sharing at all. Okay, now, for the covalent bonds, we're going to look at two different types. One is called non-polar. Non-polar is the equal sharing. These are the good little boys and girls who, when they get a candy bar or some sort of a treat, will share it exactly 50-50 with their sibling. The other type of covalent bond is polar, and this is called unequal sharing. That's probably like most of us. They will share, but not necessarily going to be 50-50. Now, the reason that they're called the term nonpolar and polar, what that means is a nonpolar bond means that the pair of electrons is centered between the two atoms. Okay, so if I was going to draw a picture of a molecule, and here's the nuclei of atom 1, and here's the nuclei of atom 2, and this is going to be my electron cloud. Okay. Yeah, I know it looks kind of funny. It's just a model, it's a representation. So the shared pair would be somewhere in the middle, okay? Okay, so they have an equal opportunity to be close to either nucleus. Now, an unequal sharing means that the pairs are closer to the nucleus of one atom. Okay, so here's my nuclei again. Okay, so you'll notice that the difference between this one is this one's kind of vaguely lopsided. It's almost sort of pear-shaped, and this one is more of a perfect oval. Okay? So in this, what that means is that the shared pair would be shifted a little closer to one atom. This atom would have to have a higher electronegativity. Okay? En will be my abbreviation for electronegativity because it's a long word to write over and over and over. Okay, so this atom must have a lower electronegativity value. So this one is a stronger attractor, so it pulls the electrons towards itself. Okay, now when we actually do some calculations, so we're going to take a bond, for example, and then we're going to go back to our value and we can determine how do we actually tell, using the numbers out of the electronegativity table, what type of a bond we have, polar, nonpolar, or ionic. Okay, so we're going to look at nitrogen to oxygen. Okay, now we're going to jump back to our table real quick, and we're going to look at the numbers for nitrogen and oxygen. Okay, the table says nitrogen is 3.04 and oxygen is 3.44. Now what you're going to do is you're going to get your calculator and you're going to subtract the two. And you're going to take the absolute value of your answer, because we're just looking at the difference in electronegativity between the two. Now, you can look at that really even in your calculator. You can see that the difference is 4.0. Okay? And it would be negative the way you set it up, but an absolute value is always a positive number. So the difference is 0.40. Now, okay, that's a number. How do we tell, though, what kind of bond it is? Well, we need some type of a little scale to tell us. Okay, 0.4 and 1.7 are our cutoffs. Okay. Anything with a difference greater than 1.7 is ionic. Anything with a difference of less than 0.4 is nonpolar. Anything with from 0.4 to 1.7 and in between. It's a polar bond, unequally sharing. Okay, so we can put it this way. Okay, less than 0.4 is nonpolar. Okay. Greater than or equal to 0.4 or less than or equal to 1.7 is polar, unequal sharing. Okay. And greater than 1.7 is ionic. You're going to have to know these numbers for your mastery quiz and on your unit test. So just make sure that you can quickly sketch out on your paper this little drawing here to help you do it. Okay, now this is 0.4, okay, so it's 0.4 or greater. Okay, so that means that this would be classified as a polar bond. Now, for polar bonds only, you have to do an extra step. The extra step is you have to put a symbol on the more electronegative end of the bond to say that this end is more negative. So that's what it means. Because the electrons are closer to that particular atom most of the time, that end of the bond is more negative. And the other end of the bond, because the electrons are kind of pulled away from it a little bit, is more positive. So we use a symbol called the delta symbol. Okay? The delta looks kind of like that. And we put a positive for the positive end of the bond. This is the one with lower electronegativity. Okay, and then the delta negative is for the atom with a higher electronegativity. Okay, so we say, okay, well, the oxygen has the higher number and it's polar, so I'll put the delta negative. That means the nitrogen has to be lower electronegativity and it gets the delta positive. Okay, now these aren't fixed, depending on if nitrogen might be bonded with something else, and the nitrogen's more electronegative, and then it's polar, and then you'll give it the delta negative. You only do this for polar bonds, okay? Because there's no positive or negative end in a nonpolar bond because they're sharing equally. And there's these symbols actually stand for partial charge. Now, in an ionic bond, there's no partial anything. A whole unit of negative charge has been transferred from the metal to the nonmetal. And sometimes it's 2 or 3 or 4, depending on the oxidation number of the metal. So you're only going to do these little partial notations for a polar bond. Let's look at a couple of other quick examples, and then you'll have the opportunity to try it on your own. All right, so let's look at sodium and chlorine. Well, if you go back to your electronegativity table, sodium is 0.93, chlorine is 3.16. So we have 0.93 minus 3.16. Remember, this is an absolute value. So you put that in your calculator, 0.93 minus 3.16, okay, and the answer is negative 2.23. An absolute value is 2.23. Now if you look at your scale, this is way above 1.7. Indeed, this is an ionic bond. It's kind of what you think about. You're saying, hey, metal, nonmetal, isn't that ionic? Yeah, but sometimes it gets a little fuzzy, especially when you talk about the metalloids. Are they more going to be metal-like, or are they going to be non-metal-like when they bond with other things? And electronegativity differences can give you a feel to that. The other reason that polarity is so important is that polarity occurs in a lot of covalent molecules, and what this does is it gives them some positive and negative-ish characteristics. So this is why pure water is not the world's best conductor, but it does conduct some electricity. And that's kind of confusing because generally we say covalent compounds are bad conductors. But if the covalent compound has lots of polar bonds in it, it might be a not so bad conductor. conductor after all. Okay? So that's why when you did your bonding lab, you might have found some compounds and you're like, hey, I think these are supposed to be covalent, but they kind of conduct a little bit. So that feels a little confusing. And now you can see why. Is that with the unequal sharing, they have this positive or negative-ish kind of ends, and that actually allows for electrical current to flow through them, because now you do have charged particles, and since covalent compounds are liquids or gases, they're moving around, and that allows electrical current to pass through the substance fairly easily. Okay, so what you're going to do in your worksheet is you're going to do this type of thing. You're going to look up the electronegativity of each of the two elements. You're going to subtract them. You're going to take the absolute value, and then you're going to use your scale to simply classify. Is it nonpolar, polar, or ionic? If you say it's polar, you have to label the two ends, label the elements, just like I did here with these symbols. If you say it's nonpolar or ionic, just skip this step. Okay, have fun.